Alright. So, now let us take a library of of components that we encounter in practice and draw their small signal equivalents, right. So, that when you next time you do not have to keep doing these derivations all over again. When you look at the element, you know what to do to get the small signal equivalent. What is basically what it means, what our theory has told us is that take every element and replace it by its small signal equivalent, correct. So, let us start. The first element that I would like to start with is the voltage source. Now, is this element a linear element or a nonlinear element? So, this is some voltage Vx, right. What is the IV characteristic of a voltage source? What will we plot on the x axis and what will we plot on the y axis? I mean, if I gave this to you in a box with 2 terminals and asked you to plot its IV characteristics, what will you do? So, on the vertical axis you will plot the voltage, and on the x axis you will plot the current, okay. So, I will call this V, and what will I see? A straight line, a horizontal line, okay. And why is this a nonlinear element? It does not pass through the origin, correct, okay. So, so what is the small signal equivalent at any operating point? So, let us say I pick this operating point. If I find dV by di at that operating point, what will I get? You get 0. So, what is the small signal equivalent? It is a short circuit. Okay. And what is the definition of small signal? Yesterday we saw that the definition of small signal depends on the operating point as well as the function itself. What comment can we make about what constitutes a small signal? This is a nonlinear element, we all agree. So, there must be a definition for what constitutes a small signal, right. What signal constitutes a small signal, or in other words, how large an excitation can I put around the operating point, okay, and expect that the small signal approximation is valid. You have the characteristic, you can check. Pardon? Yeah, in this particular case, it is a straight line. So, the first derivative will approximate it anywhere, right, and therefore, any excitation constitutes a small signal. Is that clear? Right. Here is an example where a small signal necessarily need not be small the way you imagine it, right. Any signal constitutes a small signal. You understand? Okay. All right. Next thing I am going to do, next I am going to draw is basically a current source. Let us say this is the voltage across the current source. So, when I draw the IV characteristic, how will this look like? I will plot the voltage and measure the current, and what will it be? It will be a constant with an intercept of I naught, and what comment can we make about the small signal equivalent? At any operating point, we see that di by, this was dV by di is 0, this is di by dV is 0. So, what comment can we make? It is an open circuit. And what comment can we make about the validity of the small signal approximation? Again, any voltage you put in constitutes a, any change in voltage constitutes a small signal. Does that make sense? All right. The next thing is a resistor. So, this is V, this is I. If I plot V versus I, what do we get? Get a straight line that passes through the origin. The slope is R. So, dV by di is R. So, the small signal equivalent also happens to be the same as the element itself. That makes sense because, well, the element was linear to begin with, right, and again any signal constitutes a small signal. All right. Now, the next thing I would like to do is basically let us do a diode in forward bias. So, this is V, this is I, and as we have seen in the forward bias region, I is Is exponential V over Vt. Okay, I am neglecting that Is term. So, what comment can you make about the picture in forward bias? If I plot I on the y axis and V on the x axis, you will get something like that, and at the operating point what comment can we make? I di by dV is nothing but at an operating point, say Ix, oh sorry, at an operating point Vx. What comment can we make? This is nothing but Ix over Vt and given Vx you can find Ix, all right. So, the operating point is basically this combination of Vx comma Ix is basically what forms the operating point. Given one you can find the other because you know the curve, all right. And what constitutes small signals? Let us do that. So, I, as you know, is Is or I plus small I must be equal to Is exponential Vx plus small vx by Vt, which is nothing but Is times e to the capital Vx by Vt times e to the small Vx by Vt. This of course is nothing but Ix. So, Ix plus small ix therefore, is nothing but Ix times 1 plus small v x by v t plus v x by v t whole square by 2 factorial plus higher order terms, okay, which means what? Small I x is nothing but capital I x by v t times v x, correct, plus I x by v t square times 2 times v x square plus higher order terms. So, what comment can we make for small signal operation? I x by v t times v x must be much greater than I x by 2 v t square times v x square, which basically means that the I x goes away, 1 v t goes away, 1 v x goes away, which means v x must be much smaller than 2 v t. Does it make sense? Right. So, that is what it means to say small signal. Okay. The next thing I would like to draw attention to, next element I would like to consider is the following. So, we already saw that the small signal equivalent of a voltage source or equivalently a battery is simply a short circuit. Okay. Now, let me ask you a question, therefore lead you to the answer. So, let us say I have a black box and I have black box A where I have a capacitor C charged to a voltage of 1 volt. This is box A. Now, I have box B where I have a battery which is charged to, which is whose voltage is 1 volt. How will you figure out which one contains the capacitor and which one contains the battery? Pardon? Okay, you connect a load and what happens? Yeah. So, well, the idea is that, well, if you connect a resistor across both the boxes, then in one the voltage will decrease, in the other the voltage will remain the same. Okay. And why will the voltage here decrease? Let us say you draw some current I, then the voltage here is going to be, there is some C times 1 volt was the charge on that capacitor, and as you keep drawing current out, that basically means you are removing charge, and therefore, the voltage across the capacitor plates reduce. Okay. Now, if I make this capacitor larger and larger, let us say in the limit, if I make this capacitance infinite, what comment can you make? Yeah, okay. It holds infinite charge. So, what comment can you make? Therefore, can you distinguish between boxes A and B now? And the question is, the capacitance is infinite, but charged to 1 volt. Okay. Now, can you make a distinction between boxes A and B? No. Why?
Because dV by dt will be 10 to 0, so voltage will be appearing.
Yeah. So, there is infinite charge, right, and therefore, if you keep drawing charge, it does not change the voltage across the capacitor, right. Please remember that a capacitor is nothing but a bucket which holds charge, right. So, if you have a bucket like this, and then think of it as water inside, the area of the bucket is analogous to the area of the bucket is the capacitance, the height of the water inside the bucket is equivalent to voltage, and the volume of water inside the bucket is equivalent to charge, right. If you have a wider bucket, for this, if you pour the same amount of charge, what comment can you make? The height will reduce. So, basically for the same charge, if you have a larger capacitance, the voltage will be small, correct. And if you draw water out of the bucket by making a hole here, for instance, then if you have a finite bucket, then if water keeps flowing out, the voltage will fall, right. Now, if you have an infinite bucket like the sea, right, and you go on removing water from it with a if you leak water from it, what will happen? The level of the sea is not going to change, correct. Okay. So, likewise, an infinite capacitor is identical to, is indistinguishable from a battery charged to the, or rather an infinite capacitor charged to a voltage V is indistinguishable from an ideal voltage source which has the same voltage. Does it make sense? Okay. So, now with this background, can you tell me what the incremental equivalent of between these two terminals is? So, an infinite capacitor charged to a voltage Vx what is this? It is a short circuit. Okay. And you may be wondering why this makes sense at this point in time, but going forward we will use this observation. Okay. So, to summarize our discussion so far, we have looked at what happens when you have a nonlinear network which is general, and we concluded that finding the operating point has to be done numerically. Having found the operating point, a change in the branch voltages and the branch currents can be related to each other using a linear network, and it is not necessary to write out the equations, subtract them, and then come up with a network after all, right. We saw that you can simply looking at the original network, one can draw the incremental equivalent by replacing every element in the network by its small signal equivalent, where the small signal equivalent is found from the characteristics of the nonlinear element as well as the quiescent operating point. Okay. And then we saw some commonly used elements that we will come across in our examples, and basically what do you call found their small signal equivalents. Okay. Now, another quick piece of information, right? Any two terminal element without any energy source in it, correct? Okay, is called a passive element, right? Does passive mean linear? Passivity and linearity have nothing to do with each other. A passive element is simply one which cannot generate energy. Okay. So, if you take a memoryless passive element and if you plot its IV characteristics, what comment can you remember that the convention is always that if you have voltage here, the current must flow in this direction. So, what comment can we make about pardon? V into I must be positive for a passive element, must be greater than or equal to 0 for a passive element. And consequently, the characteristic can only lie in the first and third quadrant. Okay. So, the moment the characteristic goes into the second and fourth, you know that there is some source of energy inside. Okay. So, that basically finishes the discussion on nonlinear elements, basic discussion or review of networks with nonlinear elements.